In our previous lecture, we have derived the Chebyshev method. The implementation of the method requires evaluation of three quantities. One is the function fx, the other is its derivative f prime x, and its second derivative f double dash x. Further, we also mentioned that the method is of third order, which would mean that if you are away from the exact root by say 0.1, then each iteration can produce an accuracy of 10 to the power of minus 3, so that the method is sufficiently fast for any requirement. However, in many practical problems, it may not be possible for us to find out the second derivative or even the first derivative. Therefore, in such circumstances, we need an alternative method wherein the evaluation of the derivatives may not be possible. So, in that direction we have what is known as the Muller's method, and the Muller method also uses the concept of approximating the exact root by a, in the neighborhood of the root the curve is approximated by a quadratic equation. Now, there are number of ways of writing a quadratic polynomial. One way that we have used it for deriving Chebyshev method was to write the polynomial as a naught x square plus a1 x plus a2 is equal to 0. However, an alternative way of writing a quadratic polynomial is a naught x minus xk whole square plus a1 x minus xk plus a2 is equal to 0, where we take a naught not equal to 0 because it is a quadratic polynomial. Now, if I open it up and simplify, what I would simply get is some a naught x square plus some b1 into x plus b2 is equal to 0. Therefore, this is a suitable form for me in order that the method can be derived much more easily. Now, the application of the Muller's method requires three initial approximations. If you remember that the Newton-Raphson method required one initial approximation, secant method required two initial approximations, the Chebyshev method required one initial approximation. But for implementing this Muller method, we need three evaluations, three approximations to the exact root. These three roots are any three approximations near the root. The exact root need not lie between any one of these intervals. For example, if the root is say 5, we could choose on one side of it say 3.54 or 4.7, or randomly arbitrarily one can choose, provide once we know that the root lies between a certain interval, any 3 points within this interval can be taken as the initial approximation to the root. Therefore, I would take the three approximations to the root as xk, xk minus 1, xk minus 2. That means, in order to start my the method, the implementation method, I need x0, x1, x2 to start, and then find x3, x4, x5 from the method. Now, since these are the three approximations, obviously there are 3 points on the curve, that is xk, f at xk, xk minus 1, f xk minus 1, xk minus 2, f xk minus 2. Through 3 points we can always plot a quadratic curve, that is a parabola. Now, this parabola will intersect the axis, and that point it cuts the axis at 2 points. Again, one root will be the exact, other root will not be approximating the exact root. So, what I would do, I would just substitute xk, xk minus 1, xk minus 2 in this what I had written in the previous step. So, you see the reason why we had written will be obvious now. When I substitute x is equal to xk in this, this term drops, this term drops, so a2 gets evaluated automatically. So, a2 will be simply equal to fx evaluation of this. Now, I substitute xk, x is equal to xk minus 1, I would get a naught xk minus 1 minus xk whole squared, then a1 into xk minus 1 minus xk plus a2. Similarly, I will substitute the approximation xk minus 2 here, so that I have fk minus 2, this is xk minus 2, and this is xk minus 2 minus xk plus 2 is equal to 0. These are three equations in three unknowns, a2, a0 and a1. Now, since a2 is determined, I can take a2 to the left hand side here, then I will have a system of two equations for determining a0 and a1. So, what I would do is I would solve these equations. Now, a2 is determined from this. So, to a2 is equal to fxk. I have taken this A2 to the left hand side, then I am finding first of all D as the determinant of the coefficient matrix. So if I evaluate the determinant of the coefficient matrix, that is D, that is xk minus 1. If I take the determinant of the coefficient, what I would have here is xk minus 1 into xk whole squared into xk minus 1 minus xk minus the product of these two terms, that is xk minus 2 minus xk whole squared into xk minus 1 minus k. So this is the determinant of the coefficient matrix for A0 determining A0 A1. Therefore I can find out A1 as 1 upon D into by using the Cramer's rule, I have evaluated the numerator, and similarly I evaluate for the A0, this is the numerator that comes from there. That is simply using the Cramer's rule for 2 by 2 system of equations. Therefore I am able to determine the constants A10 and A1 A2 very easily by assuming the polynomial form in the special form that we have taken there. If I had taken it as A0 xk A0 x square plus A1x plus A2, I will have to solve a system of 3 by 3 equations, and the system of 3 by 3 equations would give me the same solution, but in a different format, wherein I will have to combine the number of terms to get this particular format. But this format you will see later on, we shall be using such an approximation for a polynomial, in general a polynomial degree n, to find out some methods, some other numerical methods also. Therefore when once I determine A0 A1 A2 from here, I would go back and substitute in this polynomial. Before doing that, let us first of all simplify this D that we had written over here, because this can be simplified further. So let me just put the slide over here. So if I now simplify this, you can see that xk minus 1 xk is a common factor, xk minus 2 minus xk is a common factor. So I can take out both these common factors, xk minus 1 minus xk, xk minus 2 minus xk, and what is left out is the xk minus 1 minus xk and minus xk minus 2 plus xk. So xk cancels, I have a factor of this particular form. Now you can see that the denominator of this can easily be written down once we know the 3 approximations. You start with any approximation, either xk, that means from xk or the other end. So xk, we have the 3 points, xk minus 2, xk minus 1 and xk. So the starting one is xk minus 2 and the last one is xk, any one of them we can start. So what I do is I subtract xk from the remaining 2 previous approximations, xk minus xk minus 1, xk minus xk minus 2. Then I move to the next point in the order, xk minus 1 minus xk minus 2. So this will be the denominator. So you can look at it reverse way, you can start from the other end, you start from xk minus 2, let us take a minus sign throughout. So xk minus 2 minus xk minus 1, then xk minus 2 minus xk, that is over. So I have to move to the next point, that is xk minus 1 minus xk with a negative sign. So if I move from that sign, I will have a minus sign here. So either I can do from either side, but it is always good that we start with the current approximation that is available, previous one, that is xk, so that we do not take care of any sign. So it will be simply the product in the denominator. Now since now we have solved for A0 A1 A2, we can now go back and substitute in this. So I substituted for A0 A1 and A2 here, and once I substitute it over here, I can write down the next approximation. So the next approximation is the f of xk plus 1. Here I am substituting, now I am putting this is equal to 0. So I am putting xk plus 1 here, xk plus 1 here, this is a quadratic equation for xk plus 1 minus xk. So I solve by the ordinary method, that is xk minus 1 xk plus 1 minus xk is equal to minus 1 plus minus under root a1 square 4 times a0 a2 divided by 2 times a1. So I have just solved this equation for xk plus 1 minus xk, that is I have taken xk to the right hand side. So it is a trivial finding the root of this quadratic equation, and both the roots we are taking over here, and this form of this can be simplified by rationalizing this. So I multiply the numerator and denominator by minus the a1 plus minus under root of a1 square minus 4 a0 a0, and when I multiply it out, you can see a1 square cancels with a1 square, and I have a plus minus 4 a0 a2. Out of this 4 a0, there is 2 a0 in the denominator, it cancels. So what is left out is simply 2 times a2, and in the denominator I have a1 plus minus under root of a1 square minus 4 a0 a2. So the minus sign has been taken care of by writing this. Now there is a reason for writing this rationalization in this particular form. We have started with initial approximations xk minus 2, xk minus 1, xk. The next, since the solution is a continuous solution, the next root that we are going to get, or next approximation we are going to get, should be closer to xk. It cannot jump far away from the xk. Therefore what we do here is, in order to choose the correct the correct value to be added to xk, I would see that the change that comes here is small, because there are 2 values here. I will choose that particular value which gives me the smaller of the 2 in magnitude. So what I would do is, the sign in the denominator in equation 7 is chosen such that a1 as that of a1, so that the denominator has a maximum absolute value, that is xk changes by smaller value. Let me explain it again. We are taking the square root, therefore this is a positive square root. Now this quantity will be small if the denominator is large in magnitude. Therefore depending on the sign of a1, if a1 is positive, I will take positive sign here, then the denominator is largest value. If a1 is negative, I will choose the negative value here, so that in magnitude it is large, and in this quantity will be smaller in magnitude. Therefore that is what we had discussed here, that the sign in the denominator in this equation is chosen as that of a1, so that the denominator has the maximum absolute value, that is xk changes by the smallest possible value. This will automatically determine throwing away of the other root, because the fact that we had rationalized it and brought in this particular form, we are automatically throwing away the second root by saying the other root is going to give a bigger change to xk. Therefore that is how we have solved the problem. Now let us use this method. Now before the example, let us discuss what we have to do for the next iteration. What is the computational cost per iteration? We have the approximations xk minus 1, xk minus 2, xk minus 1 and xk. We have computed xk plus 1. Now we go to the next step. I need evaluation of fxk plus 1. I do not need anything else here, because the a0, a1, a2 do not contain any other thing. Therefore the cost of evaluation is simply one function evaluation, that is f of xk plus 1. So the cost of evaluation is only one function evaluation. However, we shall show later on that the method is not quadratic or cubic, it drops down as super linear, that is about 1.8. That is superior than the secant method, but it will be only 1.8 as the rate of convergence. We are going to discuss it again. In a sense, we want to state here that what we have derived is not superior to Chebyshev method or superior to the Newton-Raphson method. Now now let us take this example, perform 2 iterations of the Muller method to find the smallest positive root of x cubed minus 5x plus 1 is 0, and here in the problem the initial approximations are given to us as 0, 0.5 and 1. We know earlier we have shown that the root lies between 0 and 1. So we have just taken 3 points randomly, 0, 0, 0.5, 1. If it so happens, depending on the root, if you are able to take a different approximation, you may reduce 1 or 2 iterations, and if it is not, it will take 1 more or 2 more iterations to adjust and converge from one side. Now let us solve this problem. Now here we have fx is equal to x cubed minus 5x plus 1. Now I evaluate f at, I have taken the 3 approximations are given. So f at 0, that is f0, f at 0.5, that is f1, f at 1 is f2. So these 3 values are 1, minus 3.5 and minus 3. Now we have we will substitute it and get the first iteration. Now if you remember that a2 is computed as f2, that is minus 3, then we said the denominator is starting with x2, x2 minus x1, x2 minus x0, x1 minus x0. So I am starting from x2 and then taking all the subtractions from all the remaining approximations, and this of course I can compute easily, it comes at 0.25. Then when once the denominator is obtained, then the numerator also forms really a particular way of writing it. It will take little longer for me to explain, but you can see the way in which the sequence goes in the numerator also. This is f2 minus f1, x2 minus x0 whole square, f2 minus f0 x2 minus x1 whole square. So this f2 is x2, f2 x2, f1 opposite value, f0 opposite value. So this is how a particular sequence